Welcome to Looking at Atoms. In this video, we'll explore how scientists use a variety of tools to study the world at the atomic level. This field is called spectroscopy, and it allows us to see the smallest building blocks of matter by analyzing how they interact with light and other forms of energy. There are many ways to do this, so to clear them up, I've organized these spectroscopy techniques into groups based on the type of information they reveal. Group 0 includes methods that uncover details about subatomic particles, such as electrons and neutrons. Group 1 focuses on techniques that analyze individual atoms, helping us identify the elemental composition of materials. Group 2 covers methods that reveal how atoms interact within molecules, providing insight into molecular structures and chemical bonds. Now, let's explore each group in more detail. Group 0. Subatomic Particle Information Electron Spin Resonance, ESR, or Electron Paramagnetic Resonance, EPR. First used in 1944 by Yevgeny Zavoysky to study paramagnetic materials and the magnetic properties of electrons. Today, portable ESR devices start at around $20,000 to $30,000. The coolest project it's been used for is in quantum computing research, studying quantum bits or qubits and electron spins, which could revolutionize information processing. Neutron Spectroscopy. First used in the 1940s, following the discovery of the neutron by James Chadwick. It was initially used to study atomic nuclei and atomic motion, particularly for solid-state physics. Access to neutron facilities costs upwards of $100,000 per experiment at national labs. One of the coolest projects is its use at the spallation neutron source at Oak Ridge National Laboratory to investigate superconductivity and quantum materials. Photoelectron spectroscopy, PES, first used in the 1960s by Kai Siegbahn, who won a Nobel Prize for its development. It was first used to study the energy levels of electrons in atoms and molecules. Basic PES systems start around $40,000 today. A standout application is its use in nanotechnology and surface chemistry, particularly for solar cell and battery research. Group 1. Single Atom Information X-ray Fluorescence, XRF, first used in 1913, developed by Henry Moseley to determine elemental composition by analyzing emitted X-rays from excited atoms. Handheld XRF analyzers are available for as low as $5,000. It has been used on NASA's Curiosity rover to analyze the elemental composition of Martian rocks. Atomic Absorption Spectroscopy, AAS, first used in the 1950s by Alan Walsh, initially applied to measure the concentration of elements in liquids. Today, entry-level systems cost between $5,000 and $10,000. It is crucial in environmental monitoring and food safety, such as detecting toxic metals like lead in water. Inductively Coupled Plasma Spectroscopy, ICP, first used in the 1960s to detect trace elements by ionizing a sample in plasma and analyzing the emitted light. Basic ICP systems start around $10,000 today. A cool application is in deep-sea exploration to examine the elemental composition of hydrothermal vent deposits. X-ray Absorption Spectroscopy, XAS, gained prominence in the 1930s to study oxidation states and local bonding environments around atoms. It requires access to synchrotron facilities, making it expensive, typically costing $100,000 or more. One of the coolest uses is in archaeological studies, analyzing ancient metal artifacts for corrosion patterns and metal composition. Group 2. Interatomic Relations Information Raman Spectroscopy, first used in 1928 by C.V. Raman to study molecular vibrations and bond structures. Handheld Raman systems are available for as low as $3,000 to $5,000. One of the coolest applications is on NASA's Perseverance rover, which uses it to study the molecular composition of rocks on Mars in the search for signs of life. Infrared Spectroscopy, IR, or Fourier Transform Infrared Spectroscopy, FTIR, IR spectroscopy has been in use since the late 19th century, but FTIR specifically was developed in the 1940s by Peter Felget. It's used to study molecular bonding and functional groups. Basic FTIR systems start at around $2,000 to $5,000. It's been used in astronomy to study the molecular composition of interstellar dust clouds, revealing the formation of stars and planets. Ultraviolet Visible Spectroscopy, UV-Vis, developed for chemical analysis in the 1940s, it measures electronic transitions in molecules by analyzing light absorption. Basic UV-vis spectrometers can be found for as low as $500 to $1,000. It is essential for DNA and protein research, helping analyze biomolecular concentrations for genomics. Fluorescence spectroscopy. Discovered in 1852 by George Gabriel Stokes to study substances emitting fluorescence when exposed to light. Benchtop fluorescence spectrometers start around $5,000 to $10,000. It plays a critical role in cancer research, detecting cancerous cells and tracking drug delivery at the molecular level. Nuclear Magnetic Resonance Spectroscopy, NMR. First used in the 1940s by Felix Bloch and Edward Purcell to determine molecular structure. Entry-level NMR systems start around $70,000 to $100,000. Its most famous application is in MRI scanners, widely used in medicine to visualize internal body structures for diagnosing diseases. Time-resolved spectroscopy. First used in the 1960s to study fast chemical reactions. Time-resolved systems start around $50,000. It was groundbreaking in femtochemistry, a field that studies chemical reactions on ultrafast timescales, with a Nobel Prize awarded to Ahmed Zewail in 1999. Mixed techniques mass spectroscopy, MS. First used in 1912 by J.J. Thomson to identify elements and molecules by their mass-to-charge ratio. Basic mass spectrometers start at around $30,000 today. It has been used in space exploration on NASA's Cassini mission to analyze planetary atmospheres, including discovering water vapor on Saturn's moon Enceladus. I hope you see how spectroscopy helps us explore the hidden world of atoms, molecules, and the forces that bind them. Whether we're studying subatomic particles, individual atoms, or the relationships between them, these techniques are key to unlocking the secrets of the universe. Thank you for watching. If you found this helpful, don't forget to like and subscribe for more content.